The next speaker is Michael Lindsey.
Okay. Well, yeah, thanks so much to the organizers for inviting me here. I have to say, I really didn't appreciate how large the TCI community is, and it's very exciting to see all of these recent applications blossoming. And well, I'm going to tell you about some work I've done trying to theoretically understand what can be achieved with QTTs, and it, has some relation with TCI. So, okay, I don't need to spend much time on this, but maybe just a set notation. These are matrix product states. Okay, we'll typically denote the cores with A, and the external indices with sigmas. So what can be done with matrix product states? Also, you don't need to really be reminded, but there are these kind of basic primitive operations, adding, multiplying, MPO, MPS multiplication, compression. And then there's certain kind of like algorithmic paradigms, I would say, like DMRG style algorithms for optimization, TDVP style algorithms for time evolution. And then there's this extra, important ingredient, which is interpolation algorithms. So QTT is basically tensor train or matrix product state ansatz applied to a certain kind of tensor, which is based on representing a function of, say, a single variable on the interval 0, 1 with a tensor by identifying the argument x with its binary decimal expansion. So, okay, every x can be written like so. We truncate at finite depth, we get every x in some kind of dyadic grid. And so then we've seen several talks already, including the last one, which kind of go over this, so I won't spend much more time. But by identifying f with the x with its bit representation, we can identify a function f with the tensor t. And then the QTT is just, well, it's just a tensor train applied to this compression of this tensor. So I do kind of want to, I don't know, speculate or raise questions about why we would want QTT as opposed to other classical algorithms. So that's something that I've been pondering, and I don't think I've resolved. I think Jason will also be getting at this question in his talk. So yeah, okay, I'm an applied mathematician, and from like a numerical analysis point of view, this is just a very, it's a very strange thing to do, to like completely upend our usual techniques for discretizing functions, and it raises a lot of questions, like why do this, and what's the most fair comparison for any particular algorithm that you're achieving with QTT, and it's often very subtle to, I don't know, come up with a fair way of even answering that question. So the first point to address is like, what can QTT represent well, which is already subtle. So just by imposing this kind of ansatz, what structure can it reveal that may or may not be accessible with more classical function discretization tools? But then there's this other kind of, I don't know, I guess, point to make in favor of QTT, which is once you're working in this representation, okay, it's not just about whether you can represent functions this way, it's also about the kind of algorithmic toolbox that you now get access to. So using DMRG to solve linear systems within a QTT kind of framework, it looks very different from other linear solvers with, classical grid or basis representations of functions. So here then it becomes even more subtle to, I think, make a comparison. Also, the algorithms for time evolution look quite different. So yeah, okay, so those are some things to keep in mind when we're comparing. And then those points are kind of general to any kind of matrix product state based algorithm. But in specific, when you're talking about QTTs, there are also some specialized algorithms that are worth keeping in mind. And by combining all of these tools, we more or less get all of the algorithms that people are using. So convolution can be done efficiently. This is implicitly, I think, already understood in this paper from 2013, but actually my student wrote a nice blog post about it, showing how to take a QTT for a function and just kind of lift it to convolution operators. So it could be useful for some. And then there's this other kind of algorithmic primitive within QTT that has been clarified a lot in recent years, and I'll talk about a little bit, which is that the discrete Fourier transform compresses well as a matrix product operator. Okay, so now I'll get into this kind of question of what can be represented with QTTs. So yeah, what do we know for sure? Well, as people have noted, exponentials, complex or real, doesn't matter. They're all rank 1. So there's a simple argument that is kind of establishing this in one line. Degree n polynomials have rank n. So if you just are given the monomial basis expansion of a polynomial, there's formulas for the cores. I think I'll argue that that may not be the most stable way to construct a polynomial, but at least we know that degree n polynomials have rank n. Sorry?
Is it n plus 1?
Maybe, yeah. I forget, yeah. Probably that's right, yeah. Makes sense. Have a rank about n, yeah. N plus 1 is safe, yeah. At rank at most n plus 1. Thanks. Okay, so yeah, then I would say like in the kind of QTT community, most of the papers I see, they kind of take the following approach to actually constructing a QTT if they do it explicitly, which is to basically expand a function in Fourier modes or approximate it as a polynomial, or argue that it could be in principle approximated with a polynomial, and then just by summing the ranks of these ingredients, you get some rank bound on the function. And then in practice, people will often construct QTT approximations with TCI. So I think I'll also argue that these kinds of constructions are not sharp, so they don't explain, like, they don't really offer a sharp understanding about the QTT ranks. So I'll say that what I mean by that soon. And then, okay, so these are the kind of constructive techniques. TCI obviously is super powerful, but it's a little bit mysterious, under what conditions we can guarantee that it will work. Meanwhile, on the kind of non-constructive side, there's a lot of work explaining what the QTT class of functions can represent. So this paper, so I think this takes a certain perspective that it's almost like, okay, maybe let me put it this way. Like, if you just take a QTT with like random cores, you'll see that you get some function that looks really weird and rough and kind of fractal, right? So clearly QTTs can represent weird functions. And somehow this paper, maybe my take on it is like, it's kind of explaining like this weird class of functions, but in some ways that class is like, it's almost like, this is like a pessimistic area to be working in, because those functions are so weird that you could like never interpolate them from some kind of tractable number of samples.
So can you just say, what is the base of space?
No, yeah. Yeah. Okay, so some kind of like very weak relaxation of smoothness. Yeah. Okay, so yeah, but it will contain functions that are kind of like unlearnable, and that's even Noy's perspective on this as well. So then, meanwhile, there's some other work that I would say is like trying to characterize on the more optimistic side, like what are the functions we can kind of work with. And so the theory there will matches pretty well what I've done in my work, except that basically I'm going to tell you how to make explicit cores that kind of realize this theory. So I won't say much more about it, but it's very similar to the bounds I'll have. And there's a nice review. Okay, so yeah, I want to push back a little bit on the claim. So maybe not. We'll see. Yeah, sorry to be a bit of a wet blanket, but yeah, I think it's dubious to claim that QTT is offering an exponential speedup, because we need to say like compared to what. So if you're comparing, for example, to like a spectral method, like let's say the function is very smooth and it can be resolved quite accurately with Fourier modes. Well, the Fourier, the spectral method also has an exponential speed up over just making a grid that's way too large. So We kind of need to clarify the comparison when we make a claim like this. I would say that there's a very convenient thing about QTT, which is you can oversample very easily paying a very small price. So from an algorithmic point of view, it may be that this point is kind of has some merit, but from like a function approximation point of view, it's not making a fair comparison. And I would even argue that showing that QTT storage cost is not worse than Fourier series expansion is not that trivial. So that will be one of the results I'll try to explain. Okay, so yeah, now into this analysis. So before talking about how to construct cores like explicitly, I just want to explain why the ranks, why in principle there exists a low rank QTT, or in other words, explain why unfolding matrices have a low rank. But let me kind of maybe just give some teasers to get you interested. So I'll ultimately argue that, so if your function is band limited by omega, so the Fourier transform is, it's supported on the interval minus omega, omega. In fact, the QTT ranks are square root omega. They're not O of omega. So O of omega is what you'd get by just doing a Fourier series expansion. But actually, we'll have square root omega. And that's actually kind of important because the storage complexity of the function in Fourier series is omega. And a core, well, the core is rank by rank, right? So if it's anything worse than square root omega, you actually have a worse storage complexity for the QTT. So it has to be at least this good, or in fact, QTT is worse than a Fourier series. Yeah, and maybe, okay, on the point of polynomials, like one way to interpret what these cores will do is they'll be offering an explicit but numerically stable construction of a polynomial in a way that's kind of like more related to Chebyshev interpolation. We also want algorithms that can reveal rank automatically. So we'll kind of get something like that along the way. And we kind of want to close the gap in this theory, like these papers that I mentioned here, between theory and practice of those papers. So realizing those rank bounds with some concrete constructions. And yeah, maybe a more academic point is actually getting L infinity error bounds, because when you just bound the ranks of unfolding matrices, you can only get L2, at least as far as I know. Okay, so unfolding matrices. These are the things that you get by taking a tensor and then kind of splitting it across some, well, split indices into groups. And there are days that this control rank tensor is made. So if we basically take it, achieve this the house for sumeric rank, then we're explain from the function point of view by full matrix will rank some function. So the argument, if I have X, split argument to the piece, letter piece, and grade, and going to be that's the play we're coming from makes. So less basically sums all the bits up to that, and the group is over me. So I this function v max f plus 2 minus mv. That function on the interval. And if I just insert an interpretive composition, which is just kind of running my brain off and putting in v, put alpha, which are going to be Lobato nodes, but they could be anything really, your favorite interpolating grid on 0, 1. And then P alpha, the corresponding interpolating functions. Then I get this approximation. Yeah, so these are just the interpolating polynomials for subordinate to the choice of nodes, C alpha. And if you choose particular choice of nodes, you'll get very nice interpolation properties. So now if I just substitute in this formula into kind of my splitting of f into 2 arguments, I get this. So f of x is approximated as, okay, this piece, which is going to be my left factor in the unfolding matrix, low rank decomposition, and then this piece, which will be the right factor. So the left piece only depends on the lesser bits, and the right piece only depends on the greater bits. Yeah.
Small c does not depend on me.
Small c does not. Yeah, it's basically an a priori choice. Yeah, I'll have a picture soon. Yeah. So, okay, so that's the idea, and I think this pretty sharply characterizes the rank for most cases of like smooth functions. And you'll notice that actually, okay, so then you can apply like very standard error bounds for Chebyshev interpolation to explain how large this interpolating grid needs to be, which is precisely the rank that you get. Size of the interpolating grid is this size of this sum here. So you notice from this construction, like this function is getting kind of smoother and smoother the deeper we go. So when m becomes larger, the dependence on v becomes smoother because I have this kind of prefactor. So in fact, if you just use these interpolation bounds, you'll get better and better error bounds the deeper you go into the QTT. And the easiest, I think the cleanest case, which took me a while to realize, is just to assume f is omega band limited. So in the band limited case, basically these ranks basically decay by a factor of 2 every time. That's what the theory kind of spits out. You can make weaker assumptions that give something a little weaker, but basically these ranks decay by a factor of 2 each time. That means that actually gives you this square root of omega bound. And so basically what I'm arguing is you need to look at the decaying rank bounds, not just a global rank bound, to understand this. Because the reason the square root of omega happens is that you also have a trivial rank bound when you're going from the left to the right of the QTT. The first QTT rank can never be more than 2 because it has 2 rows, the unfolding matrix. Next one can never be more than 4 because the unfolding matrix has 4 rows, 8, 16, etc. So you have this trivial bound that's getting bigger, and then you have this decaying bound that's getting smaller. The crossover point happens when this 2 to the minus m omega is equal to 2 to the m, and that gives you square root omega. So the point where the trivial bound and the non-trivial bound cross over. So this is the result, somewhat stylized presentation. And okay, so then we can conclude that we're not doing worse than grids for band limited functions. But I think there's no simpler way to see this. Okay, so then, yeah. So how do I turn this into a direct construction of cores? It's a little bit, I need like a little bit of an extra ingredient. So I need to recursively deal with this tensor, which I'm calling s less equal 3 here, so that the 3 is for I have 3 cores so far. And it's basically like the function on the bits I've seen so far, but then I have this extra index alpha, which is the hanging one here, which is an additional, it's like an additional index for a Chebyshev or just arbitrary interpolating grid on the next level. So this tensor contains information for all of these. So every kind of like little cube indexed by these leading bits, and then within that cube, an interpolating grid inside that cube, indexed by the hanging edge alpha. And so I want to recursively get the next thing, so s less equal 4 in terms of s less equal 3 by like attaching a core. So how would I do that? Well, what you want to do is you want to take a function where we zoomed into one of these like little squares or just intervals in the dimension 1 case. And I want to take the function values on this these Chebyshev Lobato nodes on this interval. Then I want to interpolate the function values on the Chebyshev nodes for the next subinterval in 2 cases, either the case where I interpolate onto the kind of left bit or the right bit. So I want to construct basically a tensor that does the following thing. Depending on the control bit sigma, it will interpolate these values indexed by alpha to these values beta, or in the other case where sigma equals 1 to these values. And that tensor is just I'll do it by polynomial interpolation. So I'll interpolate this function to here by plugging in the polynomial interpolation, and then evaluating at these output points. This is a formula that I need. So in the sigma equals 0 case, it gives me these ones. Sigma equals 1 case, it gives me these ones. So there's this one core A that I can construct, and then I can just keep attaching it all the way down, and that will extend my initial just grid evaluation of the function to a QTT at all depths. So ultimately, I get a QTT that looks like this. Then I have to think a little bit about the boundaries, but let's not do it right now. So then the nice thing is I can make this construction kind of rank revealing. So I can assume recursively that as I keep attaching cores, I've already kind of gauged my tensor train as such, where these U1s and U2s are unitary or have orthonormal columns interpreted suitably. And then I have some leftover piece R. So then when I attach this new A, I'll do the following, sequence of operations. So I lump the R that was hanging from before with the A, I get this B thing, do an SVD, then I lump the, sigma V parts of the SVD into the next R, and then I'll repeat. So usually this would be a dangerous thing to do because you kind of need to make sure that you're right, the right part of the train is also gauged. Otherwise, when you start making compressions, you can't control the error that you're incurring. However, here everything's fine because the cores that we're going to attach later on, these are just doing ultimately a big polynomial interpolation, and I can bound basically the amount that could expand errors in terms of this theory of what's called the Lebesgue constant. So this is kind of like the operator norm of polynomial interpolation, and this grows only logarithmically with the number of points. So you can get an optimistic control here that justifies doing this rank revealing on the fly. Okay, so then this can be formalized in some theorem, which maybe let's just gloss over, but roughly speaking, I can, as long as I'm willing to use a little bit of extra buffer, I can explicitly make these interpolation ranks to decay by a factor of 2 every time, but add some little buffer delta, and that delta has to grow like very weakly with the depth in order to make sure that all this stuff doesn't, in order to get some constant error. So then there's a few gadgets I want to explain. It turns out it's possible to replace these cores with sparse approximations. So if you're doing a really big grid, this could be worthwhile. Okay, this is a really nice paper, by the way, and it's this is a little bit of a confusing point, but I also tried to explain it in my paper, so happy to talk about it. But yeah, just for now, suffice to say, I can make these cores sparse when they're very large.
Something you have to do actively, or just happens by itself?
Actively, yeah. So there's some a priori construction of these A. Yeah, that means that I can make the cost of this rank revealing algorithm what I would guess to be optimal. So O of n r squared, where n is the number of points in your grid, and then r is the revealed rank. Okay, then I'm just going to not talk about multivariate case, but happy to talk offline about it because there's so many options and intricacies. But the last thing I want to mention is, yeah, we can kind of invert this construction. So this gives us a way to take like grid values of a function and then kind of unzip into a QTT. But for some algorithms, like maybe you're solving some nonlinear PDE or something, I could imagine there's a reason to want to go back and forth where you can apply like pointwise nonlinearities on the grid and then zip and unzip to do your favorite operations in each representation. So this can be done. Basically, you do like a little bit of interpolation at a very small, at the very deep part of the QTT to kind of open up this extra leg, and then you keep applying these particular generalized inverses to kind of undo the construction. So there's a way to zip back and to recover your grid evaluations. Then the other kind of extension is basically to say that, okay, now what this does is it takes like the evaluation of a function on some interpolating grid and then it unzips it into a QTT. But actually this can be done on a like multi-resolution adaptive grid. And so at a very small overhead cost to the bond dimension. So yeah, consider this situation where you have a function with like some sharp peak, but everywhere else it's kind of not that bad. So at every level, you're going to look at like which intervals are too dangerous to interpolate on. So at the first level, there's 2 intervals, and this left one in red is too dangerous because it contains the sharp peak. The next level, only this one is dangerous because that's the one that contains the sharp peak. The next level, this one, the next level, this one, etc. So if you have a bound of Q, like how many dangerous subintervals there are at each level, you can explicitly build cores that only interpolate on safe subintervals and otherwise like defer interpolation until later. So there's this kind of like cellular automaton like construction where at every level you're passing along the information of both am I in a safe interval yet, and also if I am, like what are my grid values that I want to interpolate to the next level, and this can all be built into cores. So at the end of the day, you get whatever error bounds you have for an adaptive grid on some like dyadically refined adaptive grid for polynomial interpolation on these refined patches would carry precisely into the error bounds that you get for your function. So yeah, you can deal with cusps or very narrow Gaussians or anything. Yeah. Yeah, have to know. But okay, then you could imagine trying to. So then, yeah, in applied math, people have thought a lot about how to like construct adaptive grids. But that's a separate question. Yeah, and I guess a more deep point would be like if you're running DMRG or something to find a QTT, it might find this like for you. This is just giving a bound on the bond dimension, so you hope that it will find the structure for you. But if you wanted to just directly interpolate it, you need to know it. Okay, so I'll just give a few simple demonstrations. So if I just take like a random Fourier series with potentially like very high frequencies, okay, I'm comparing to like the oldest version of TCI, so I know people can do better now, but eventually I can break its stability by making some very oscillatory functions. And you kind of, yeah, like, and I would just also say it's not like a very fair comparison. Like we have a lot of information that we're exploiting that TCI doesn't, because it's like this black box that knows nothing. But if you have this information, you may as well use it. So you can really economize on the number of function evaluations to interpolate a function. And we can do so stably. Okay, it's not that interesting because it kind of just matches the theory, but there's a bunch of demonstrations in the paper that kind of explain, well, yeah, validate what the theory is saying. So this one in particular is explaining how the multi-resolution construction can give you a pretty sharp bound on the rank of a Gaussian that's independent of the width of the Gaussian. So if you make your Gaussian very narrow, it's actually becoming very non-smooth, but the rank is actually not increasing, and that it's captured quite sharply by this adaptive grid construction. Okay. Yeah, 5 minutes? Okay, great. Yeah, so then very quickly, I just want to kind of highlight something kind of related. So this is work with Chris Chen on the discrete Fourier transform or quantum Fourier transform. So yeah, okay, the discrete Fourier transform you can write like so, where S and T go from 0 to n-1. And if you identify S and T with these bit strings, but with reversed order, then the famous fact is that the discrete Fourier transform becomes a low rank MPO when viewed like as such. So it's very important to reverse the order or it doesn't work. And okay, this perspective has been developed over a while. Most recently, I think, sharpened a lot in my collaborator Chris's work with Miles and Steve White on this paper that says that QFT has low entanglement. So they show that the unfolding matrices of this tensor are actually low rank. But I think what I just want to say is something very spiritually similar to the first part of the talk. Like, can we construct cores that like match what the theory is telling us about the rank pretty sharply? Okay, and so you can, and you still use polynomial interpolation. So this is kind of the key diagram. So the discrete Fourier transform, you can just do some algebra to split it as such. So where there's these smaller Fourier transforms. And this middle block is like the key kind of integral kernel you want to interpolate with polynomial interpolation. So it has this x greater, y less. And if you insert a polynomial interpolation to interpolate the x part from some C alphas, that's the key thing that controls the rank. And so whatever the rank is of interpolating this kind of integral kernel, which is it's smooth and it doesn't depend on anything, it's just some fixed thing. That's the rank of the QFT. You know, it turns out to be not that high, like 15 or something. So yeah, so we can show this, and then there's to get the actual explicit cores, there's something very similar. You need to like recursively construct some tensor that you can then extend by attaching another core. And at the end of the day, what's kind of amazing is like there's just this one core that you can create. It's not very big, right? So this will be like, you know, 20 by 20 by 2 by 2 tensor at worst. And it's the same core, A. And this is the formula for it. And if you just attach it to itself and then like put these boundary conditions, that's it. Yeah. So it's just one core. I mean, I know people could already construct this pretty well in practice, so maybe, yeah. But it is, if you had to do it again from scratch, I think probably the cleanest way. Yeah, so there's some interesting points to make that are fleshed out further in the paper. So one interesting thing is that the approximate quantum Fourier transform, which is like a kind of, it's like a quantum circuit for doing QFT that basically leaves out long-range gates. It actually is exactly recovered in this framework, but where you use like a very simple interpolation rule. So now, in some sense, what we're doing is like improving the interpolation rule. However, it doesn't actually then lead to an obvious quantum circuit. So it's kind of an interesting open question whether you can come up with better approximations that could be implemented as quantum circuits. So finally, yeah, I just want to conclude by saying interpolation is, as everyone else is saying, a good framework to think about. And in particular, it allows us to leverage smoothness in understanding QTTs and even the discrete Fourier transform, and going back and forth between grids, maybe adaptive grids and QTTs. The questions I'm really interested in are, so first, if we take these functions and their Fourier transforms, I can't think of any useful function I've seen thus far where we emphatically know that it has a low QTT rank. So if you know of such a thing, it creates some open question about how to understand this. But so far, I just don't know that I've seen anything that clearly demonstrates a function sitting in this gap between like what we understand about how to deal with computationally and then the weird stuff like the Bezoff space stuff. And I'm really interested in whether we can like get some emphatic, like theoretical computer science style, even though that's not always my style, like a provable advantage of QTT for some well-defined problem against, you know, all possible competitors. That's something I'm thinking about. Yeah, I can say more about where I think it's most likely, but yeah, that's kind of what I'm thinking about. And yeah, just generally in higher dimensions and thinking about how to learn functions from limited interpolations, I think this is interesting to think about. And in some sense, this work, it's basically saying like if you already know the right points to interpolate, then you can construct QTTs. So that perspective is kind of more general, I think. And TCI is giving like a way to find good points for interpolation. But are there other settings, maybe even high dimensional settings, where we know these points a priori, or where we can kind of avoid that part of the work that TCI is doing? I think is interesting to consider. All right, that's it.
Thank you very much. I think we have a question from the chat. Right. So the question is from Juan Manuel Henning. Is the QTT construction the definition of the tensor core A specific to the Chebyshev interpolation?
Not really. Yeah, you could use any. It doesn't really even have to be polynomial interpolation, but that tends to be the best systematic way to interpolate. So those are the ones with the best bounds. Yeah.
Thanks for a very inspiring talk, Michael. I'm intrigued by the last point, higher dimensions. For many of us, use case is high dimensional situations. So what are your perspective of extending your detailed analysis to that case?
Well, there's kind of like naive things to do. Like if it's still not high enough that you can just put down a grid, right? But yeah, beyond that, I don't know. It's mere speculation. But yeah, maybe I shouldn't answer more generally. But happy to discuss.
Thank you very much. I'm intrigued by your interpolation construction for Fourier transform operator. So if you go back to the slide visit,
This one or this
what
one?
you showed is like an explicit formula for the core. And I'm wondering, what does it mean? Can you just write down the MPO construction for Fourier transform operator? And if yes, what are the bond dimensions?
Yeah,
Is it
so,
exact? Is it approximate?
So it's approximate, and the error is basically controlled by the interpolation error of okay. Is there a marker somewhere? So this is like the key kind of integral kernel. So like k of xy equals e to the 2 pi I xy, where x and y lie in 0, 1. So if you can factorize this integral kernel as like a low rank kind of, across the xy splitting, then whatever rank that is, that's the rank of the MPO. So it turns out that this can be done by basically doing a polynomial interpolation of one of the variables with a rank that's pretty small to get machine precision, like no more than 20. And so then in this core, the size of these alpha and beta indices are that interpolation order, so like 20.
Thank you.
Okay.
Thanks for the talk. I would just like to highlight some related work that may be interesting to you. There was a big work done by Christoph Schwab and Vladimir Kaziev. So basically, if you want, not only in one dimension, but in 2 dimensions, so basically what is shown in his PhD dissertation, that if you have, for example, elliptic PDE with sufficiently smooth coefficients, then you can approximate the solutions to these PDEs with exponential convergence. And rather, I think that's the largest class, at least the reasonable class that I know. And the technique that has been used there is based on HP approximations, not Chebyshev, but HP, because the power of QTT is not for smooth functions, because then you can have spectral methods when you set, but the power of the QTT is when you have singularities. If you have a point singularity, like 1 over x or logarithms, they have low rank in QTT. So everything that can be represented as pointwise singularities, or maybe line singularities aligned with this QTT transposition, plus smooth function. And basically that, I think, is the largest class where it's powerful, because if you have even a point singularity...
I would argue that those ones are covered by adaptive interpolations.
Yeah, they are covered by adaptive interpolation, covered by HP methods when you have large block. The problem with HP is that every new equation requires a new PhD dissertation. That's what Christoph Schwab told me. Just construction of the algorithms for HP for every new type of problem takes a lot of time. And QTT, formally, you just take a very fine mesh. The convergence on a uniform grid can be h to the power 1/4, for example, depending on the angle, how the solution goes. But again, you can, and Vladimir here actually has some follow-up papers because of scaling up to 2 to the power 50 with Markus Bachweier. So maybe you can just check out.
Yeah, I think that work is related to these ones, like the Lars Grossedieck's paper that I cite here.
Yeah, so, but I also had a paper which is called Constructive Approximation in 2011, which covers more actually than Grossedieck. So it has exponentials, it has sort of a general, if you have a function such that f of x plus y is separable, then you have low QTT rank. And I think that's more or less.
But I guess I would just say I still haven't seen something that is not covered in the class of things you could do with some adaptive interpolation. Yeah, maybe you have HP on the subintervals that can still be achieved by interpolation. So there has to like Sobolev space, some kind of smoothness.
Yeah, and you can actually build even a non-smooth function that can have low QTT rank. So for example, if you take any dilatation equation like wavelets, which satisfy omega of 2x equals, you can easily show that with factor 2, you can easily show that QTT ranks are bounded.
Yeah.
But no adaptive thing can do it because it's like almost fractal.
Well, yeah, we can discuss. I think there's still some
we can discuss,
gap.
but anyway, I think for 2D this work, it's not a trivial work. Yeah, they got like best PhD thesis in ETH, and it's really a very like 70 pages, 70 pages mathematical formulas of deriving, and that's not trivial. Generally, it's simple, but putting all the bounds together, and it's difficult. So.
Well, yeah, if you do believe adaptive grid works, so if there really just are point singularities, there is a simple bound. Yeah. So, and that, as far as I know, it really covers all these cases.
No questions.
What about discrete data? So there are some talks and some applications involving discrete data, like this super moire system talks KPM. Where maybe there's some structure in the discrete data. Do we have other ways of sort of dealing with those situations?
Like you just have some evaluations on scattered points or something.
Yeah, like you have values on a lattice. What can we do there?
A lattice, well, lattice is, you can kind of, okay, so then, yeah, one thing you could do would be like locally interpolate to get it lift to some Chebyshev grid, and then, yeah, so if you believe your lattice is exhaustive, you could kind of shoehorn it into this framework. But yeah, if you just have truly like scattered points and you want to kind of interpolate according, in some smoothest possible way, that's something I'm thinking about.
I see,
currently.
but maybe you could take the lattice points and use, smooth out by.
If you really had a uniform
treating them
lattice,
as an under,
I think you could shoehorn into this framework.
Yeah, okay,
Yeah.
I see. Thanks.
So is it a fair statement to say that, okay, there are many cases where we add previous methods that would outperform or at least do as well as QTT, but the fact that QTT is completely agnostic gives it an advantage? Like, for instance, if you have like a homogenization problem, so you would have things at small scales, things at large scales, and you don't necessarily know in advance essentially where, like you could have like a very large bandwidth, but with a lot of it would be like very, very small. And you wouldn't necessarily know in advance. On the fact that everything is agnostic in QTT, you don't actually need to care. It's going to
Yeah, so I think
that gives it a large advantage, at least in practice.
It seems, I agree that yes, especially things where maybe you're not using interpolation, but you're just optimizing over, using DMRG or something.
Yes, because we always do.
So then in that case,
this is the initial stage to set the stage, and then you do something with it.
Sure, yeah. So in that case, yeah, you don't even need to know anything I did. These bounds are good enough. They'll just assure you that there's something lowering. I would still say though that, okay, after thinking pretty hard, it's a little murky even in this case, like when you're just thinking about what the rank bounds say and what the algorithms are and their costs with respect to the bond dimension, that there's like I haven't discovered a clear win on some well-defined problem, but yeah, that's the tantalizing thing, I think, is that the structure will be revealed and you don't have to find it automatically. I guess I would also say that perspectives differ a little bit on whether, yeah, an adaptive grid is a hard or easy thing to do. So I think for this community, you're all more comfortable with tensors, and okay, so, but yeah, maybe just here's like the prototypical problem I would say where people can duke it out is like, yeah, Poisson problem, Poisson equation with like maybe some singularities on the right hand side. Like, okay, we have, yeah, if you just do the comparison of knowing what the ranks are and knowing what the cost of DMRG is, like I couldn't find a clear win over adaptive grid, finite element kind of approach. But it's interesting to consider. Of course, in high dimensions, the nice thing is that this plugged, the QTT framework for a single variable, it pops in quite nicely to like functional tensor train approaches. And then if you have some miracle where there's low entanglement between the variables, then of course you can exploit that. But then that's sort of fundamentally more mysterious, I think.
But we are never interested in 1D.
I know, yeah, but okay, so I would say if you do the interleaved ordering, like it looks closer to this theory. If you do the sequential ordering or the comb kind of construction, then you're relying on something else happening, which is there being low entanglement between dimensions. That can be captured with this theory if you make those assumptions, but understanding that a priori, I think, is difficult.
One last question.
Just a general question. So I understand that these interpolative methods are very powerful. On the other hand, we heard this comment by Dieter Jaksch that huge amounts of computational resources worldwide are burnt on solving turbulent flow and things like that. To what extent do the people that burn these huge amounts of computational time use these fancy interpolative methods? Do you have any insight into that?
Like,
or?
sorry, for what kind of problem?
Well, if you have to solve fluid dynamics, right? So he told me that huge amount of computational time worldwide goes into that. I guess these are companies like Boeing or whatever that simulate drag of their airplane wings, etc. So I don't know, but to what extent do they use these methods? Yeah, but why? I mean, if there are these very good interpolative methods.
Well, I think, yeah, you have to think really carefully about what these ranks are and what the cost of like DMRG is in the rank, and it's just not super clear that you get an advantage. I can't comment so much on fluids, but like the one I've maybe thought, it's similar that I've thought about hardest, and I know a few people, some in the audience, and some elsewhere who worked on this, trying to push it as hard as they can, but like trying to solve a Hartree-Fock or density functional theory with QTT. So far, it just doesn't win, over like a kind of more classical approaches, and just because the ranks are low, like, doesn't mean that it's the best method. In short, you have to compare in more detail. Yeah, maybe another.
But that wasn't really the question. I'm asking people you made a comment that they don't use adaptive methods. So you said they just use finite elements.
They use finite elements, but the best one
But
is
why?
multi-grid. So
people use adaptive mesh dynamic.
no, but okay, but not based on this kind of.
Yeah, but the problem is also okay. Can you apply this method for the situation where you have a very complex geometry of the domain?
That's another thing to consider is boundary conditions are a bit of a menace for QTT.
That's an important question.
But even like, let's say density functional theory with open boundary, you've got some singularities, but they're point singularities. Okay, you still go head to head against like adaptive finite element. It's tough to beat them. Just by now the QTT somehow you can implement overnight if you're really good at tensor stuff. But okay, maybe that's an overstatement because there's a lot of pieces. But yeah, it somehow, I think from a certain point of view, seems less daunting, but it doesn't mean that it wins.
Can we discuss over coffee? Let's take a speaker again.